So with this bridge, what happens if there's flooding? Like, because you look, there's all these houses there. It looks like the water's pretty close to the top, right? And living here in Huntington, we're all innately familiar with the issue that sometimes the water levels go up, sometimes the water levels go down. So it was a really good question to look at this and say, seems a little risky. But it turns out that it's the Elbe River that is where water drains to. And so it's this lower level river that the water levels are fluctuating in. And they have to pump water up into this elevated canal. And so there's only water in this canal because they're putting it in that canal. And it's not receiving any of the runoff from the area. The runoff isn't going to flow up the berm and into this into the canal. It's flowing downward into the Elbe. But nevertheless, I thought it was a really good question to consider the proximity of residents to this and just kind of wonder, is there a risk there? And there's other risks there. It's not necessarily stormwater flooding risks, but the earth can always do unexpected things, and there could be spillage from there into it, but I don't think that flooding itself is going to be a problem. So that was a good question. I welcome thought-provoking questions like that. Let's begin by looking at these announcements. Homework 1, which is available now on Blackboard, is due on Wednesday. Now remember that Monday of next week we don't have class. So if you've got questions for me about the assignment, you can send me an email, you can call me on Teams, you can stop by my office, but you won't be able to see me in person on Monday, although I will be in the office on Tuesday if you want to come by on Tuesday and ask me homework questions. Today we're going to continue talking about flow resistance, which is sections 1 through 3 in the textbook, chapter 7. Any schedule or announcement related questions before we get into it? So I got an interesting question on my YouTube channel from Monday's lecture. I realize I haven't yet posted the link to my YouTube channel on Blackboard. I'll do that today. But I got somebody who looked at the picture of the reservoir that I showed you and they said, oh, that's Oroville. And it reminded me, yeah, that is Oroville. The name of the lake I wasn't able to remember during the lecture on Monday. But so I mentioned that reservoir is full now because of all the rain that they'd been receiving in Northern California. And I verified that that's true. Yeah, the reservoir is full, but I didn't realize quite the scale of it. It's really interesting how much that reservoir has filled up. Now this is a prior time that it went through that cycle of relatively wet conditions in 2011, which is about when I went and saw it, to a few years later. If you look, the same basic location, here's the parking lot, here's this little floating bridge, and obviously the water levels are a lot lower in 2014, and they stayed low until recently. So just a couple of pictures that illustrates the difference between when this reservoir has water in it and when the water levels are relatively low. Let me dim the lights so that it's easier to see these pictures, because there's a few interesting ones here. Try not to fall asleep with these lights down. I know it's just after lunch, but obviously when the reservoir doesn't have any water, it's not able to provide any hydropower benefits, and this reservoir does have a pretty significant hydropower generation capacity. But it is able to provide flood protection, which is another purpose of this reservoir. Is there are a lot of communities downstream that historically would have been threatened by wide fluctuations in the river levels, and so they can trap water and let it out at a more moderated flow rate and provide flood protection. And so, when the water level is down like this, I guess if we're trying to be optimists, we could say, well, at least it's got plenty of flood protection available, because they could trap a lot of water when the levels are that low. Now, consider this, just one more picture, but recently, as recently as the day after Christmas, the water level in the reservoir was 673 feet. That's the elevation of the water above sea level. That's not how deep the water was in the reservoir. That's just the water level was at 673 feet above sea level. And then January 9th, which was that Monday, 2 days ago, it was at 735. So just in a couple of weeks, the water level went up 62 feet. That's just incredible considering the surface area. We're not talking about a swimming pool that fills up quickly. We're talking about millions of acre feet of reservoir that went from almost empty to almost full. So, I mean, that just kind of puts in perspective how rainy it's been in Northern California recently. So this is the dam that is at the end of Oroville Lake. It's a really interesting dam because it's the tallest in the United States, but yet it's an earthen dam. And you'd think maybe for such a tall dam, 770 feet from top to bottom, maybe they'd need concrete, but apparently not. They can do a lot with just an earthen dam, and it's behind it the second largest man-made lake in California, 3.5 million acre feet. And that's maybe not a unit that you're familiar with, acre feet. I mean, it is what it sounds like. Acres is a unit of area. So if you had 1 foot of water that covered an area of an acre, that's 1 acre feet. So an acre is pretty big, right? This dam holds back a reservoir that has a capacity of 3.5 million acre feet. So it's a lot of water is the point. Now, it's interesting. The water can get out of this reservoir 3 different ways. The water can go through the power plant, and 16,960 CFS can go through the power plant at any given time. There is a river bypass that allows for fish migration, and that's a relatively lower flow rate, 5,400 CFS. There's this service spillway, which at its peak is able to discharge 270,000 cubic feet per second. And when the water level gets up to an elevation of 814 feet is when water begins to go through that spillway. The gates can pass it once the water's that high, but if the water's not that high, it can't go through the spillway. And then there's an emergency spillway here. Like if the regular service spillway is damaged or isn't able to hold enough, isn't able to accommodate all the flow, then water will go over this crest in an unregulated manner and just down the hillside. So recently, the storms that they've been having in California, it's not the first time that they've had heavy rain in Northern California, and it's not the first time that Oroville Dam has been on people's radar. Back in 2017, there was a storm in the watershed that feeds this reservoir that there was, it's estimated, between 130,000 CFS up to 190,000 CFS entering the reservoir. So that's how much was coming in. So obviously, if that much is coming in, either the water level is rising or they're having to send water down the service spillway because the hydropower and the river bypass combined isn't going to be able to discharge this much water. So that's exactly what happened, is there was so much water coming in, the reservoir filled very quickly, they're sending as much as they can through the hydropower and river bypass, and so now water has to go down the spillway. So what could happen, right? Well, ordinarily, water goes down that spillway at quite a high velocity. 700 plus feet is the vertical distance that the water has to spill off. There's a lot of energy that gets picked up by water as it's accelerating down the face of a concrete spillway. They've got these big weirs at the end of the spillway to kind of dissipate energy, to take the impact and the brunt of the water so it doesn't totally scour the river downstream. And what they noticed was there was a little bit of a problem, that a variety of factors caused a crack in the concrete. The factors are that, number one, they didn't inspect it probably as often as they should. Number two, it was a bit old to begin with. There were probably some construction problems. The rock underneath is weak. And so this event happens where they're having to send a lot of water down the spillway. A hole forms, so they turn off the water briefly just to get in there and have a look. But they can't turn the spillway off for very long because the water level's rising. There's still water coming into the reservoir. They can't stop that. So they have to turn the spillway back on again. The hole gets bigger, And just to give you an idea of how big that hole was, you can see for perspective here, it got up to 300 feet in diameter during one of the periods where they turned off the water and sent people down to have a look. So 300 feet, that's a big hole in the spillway. And you can see that, I mean, compared to the size of the hole, the thickness of the concrete, it's maybe just seems like wafer thin, very thin concrete. I'm sure at the time it seemed adequate, but what happened was just the condition continued to deteriorate, and water was flowing down the side, and that's bad because it was headed in the direction of the dam, all this scour. So people were wondering, is this dam going to be threatened? If this whole hillside erodes and collapses, is the dam going to be stable? And they thought probably the dam will be stable. They thought probably it will. But probably isn't good enough when you've got 180,000 people living downstream of the dam. And so they evacuated 180,000 people, in part because maybe this hillside will fail, but the other issue was that when the spillway couldn't handle as much flow as they wanted to, like they turned the flow down a bit out of the spillway, still sending some water, but they knew if they turned it all on, it was going to cause just irreparable damage. So they turned off some of the flow to the spillway, turned it down a little bit, and they're sending water over the emergency spillway, which had never been used before. First time in the history of this dam that the emergency spillway had been having water go down the front of it. And the hillside is not concrete, it's just vegetation and soil. And so you can see the scale of the destruction. They had a few hours notice, so they send guys with chainsaws onto that hillside to cut down trees as quick as possible because they knew that the water would do it, and then those trees are going to go downstream and clog things up. So they tried as much as possible to clear the area out of debris and obstacles that were going to get washed away. But you can tell from the color of the water, it's a deep, rich, dark brown, that it's taking a lot of sediment with it. So they turned on this emergency spillway. There's still water going down the service spillway. The water levels are continuing to rise, and the toe of this emergency spillway starts to scour and erode. And so they're thinking, well, if that happens, and if there's just a total uncontrolled release of water from the reservoir, then those 180,000 people downstream are in real trouble. So ultimately, why they evacuated them was because they were worried about the emergency spillway completely dematerializing and all of the flow coming out of the reservoir in just a catastrophic and unregulated way. So Oroville Dam has a real sordid history. They have repaired it since this 2017 event, but this kind of gives you an idea of the path that the water was taking through the emergency spillway as it was working its way downstream. And here you can see the size and scope of that hole. And this is vertical exaggeration, so you can kind of maybe just sense or see the path that the water was taking and how it was guided by the contours of the land. And so there was a pretty substantial hillside between the spillway and the dam, but they didn't want to take a lot of chances because so many unexpected things had happened already that they displaced those 180,000 people. So you can see here, looking downstream, the emergency spillway water making its way into the river, and all that sediment turns out not so good for the environment. Really tough for fish and other aquatic species to recover from that much soil getting into a river. It interferes with habitat. Big quantities of sand will settle out of suspension at slow parts of the river. So now suddenly they've got big gigantic sandbars and sediment in places that it wasn't previously there. So the area was pretty devastated after the fact. You can see that most of the spillway was damaged, and a lot of the rock to the side of the spillway was damaged. You may wonder, boy, how much does it cost to recover from something like that? $1.1 billion, it turns out. $1.1 billion. And the thing that's a little hard to swallow is that this wasn't a real surprise, this whole incident. There were environmental groups who had back in 2005, when this dam was getting its license renewed, environmental groups had objected to their license renewal, saying that a previous engineering study had identified too much risk. Like there was a study in 2002 that said, you know, the emergency spillway area will be damaged if there is overflow, and it'll cause all these environmental destruction effects downstream. And so it was kind of known that they didn't know that the main service spillway was going to crack, but the report from 2002 did say if this emergency spillway is ever used, it's going to be a real problem. And so they said, let's not relicense this dam until they put concrete cladding on the emergency spillway flow path. And ultimately, the dam operator didn't have to do that because the cost was going to be too expensive. It would have been $100 million to put concrete on the side of the emergency spillway. And they didn't want to spend $100 million because it's easier. What's that? Well, you know, they say a penny of prevention is worth what is it? A dollar of cure? No, ounce of prevention is worth a pound of cure. Anyways, they should have spent the money. Yeah, it would be good investment. It probably wouldn't have prevented the spillway, but from the main spillway from damage. But a study after the fact, the Association of State Dam Safety Officials considered the situation, and they said, you know, an incident like this doesn't happen just because one thing went wrong. They say the same thing is true about plane crashes, that a plane doesn't crash because one thing went wrong. A plane crashes because you've got like a tired pilot at the same time as there's weather, and also there's a mechanical failure, and then maybe in addition to that there are some communication difficulties between the pilot and co-pilot, like a culture of hostility or something. It usually takes a few overlapping problems to cause a real spectacular disaster, and that was the case here. The overlapping problems was, number one, they didn't recognize and address design and construction weaknesses. So number one, it was poorly designed, it was poorly constructed, and nobody noticed. So all three of those things have to happen for this to be a real problem. But then on top of that, it was also that the rock that the spillway was built on is of poor quality, so poor quality foundation bedrock. And then on top of that, the spillway had deteriorated. So that concrete had worn out, there were cracks in it, and they hadn't been repaired. So all of those things had to pile up for this to be such an issue. So I think it'll be interesting to see, you know, last time they had real wet weather, suddenly the water levels rose in Oroville was 2017, and then recently the water levels rose really quickly at Oroville. Hopefully they've sorted it all out, but you never know.
What can that handle? Like how high?
How high can it go? 901 feet is when flow starts going over the emergency spillway. And so in theory, it shouldn't get but a couple of feet higher than that. You know.
Have you shown this before? Like, did you show it in economy?
I don't know. Not sure.
I remember seeing this. I don't remember if you showed us or Dr. Nas showed us.
Yeah. Bad situation, right?
Yeah.
All right. Let's do some calculations. Where we left off on Monday was talking about the Moody diagram. So I have a handout for you, and we are going to do some calculations. Moody diagram. So this example says that the flow is going 30 meters per minute through a 0.25 diameter meter pipe, and the equivalent sand roughness, this K sub S is the equivalent sand roughness. So that's just saying the material that they used for the pipe, if you're going to express the roughness of that material with an equivalent diameter grand of sand, so this is like, it's a cast iron pipe, but it's equivalent roughness to a sand that has a diameter of 0.26 millimeters. So let's go through the process of determining what is the F value that should be used in a situation like this. Did everybody get a copy of that handout? And were there any extras? Thank you. Okay, so first things first, the flow velocity, V is 30 meters per minute. And so that is 0.5 meters per second. And now this K sub S is 0.26 millimeters, and the diameter is 250 millimeters. We need to put those in like units because over here on the right side of the axis, we need the ratio of K sub S to D. And so it should be the same units when we put it into that ratio. So the K sub S to D ratio is 0.26 millimeters divided by 250 millimeters, and so that is 0.00104. Okay, so that tells us which of these curves to use when we're going leftward on the diagram. So we're going to be just barely above this line right here, the 0.001. So you see how this actually starts curving upward. We're going to follow that curve to the point that it intersects whatever the Reynolds number is for the flow. So we need to determine next what is the Reynolds number that applies. So we know the flow velocity, 0.5 meters per second, and we've got the formula down here for Reynolds number, and I've described the kinematic viscosity of water is 1 times 10 to the minus 6 meters squared per second. So let's find the Reynolds number. RE is velocity times diameter divided by kinematic viscosity. So that is 0.5 meters per second and 0.25 meters diameter divided by 1 times 10 to the minus 6 meters per second. Oh, meters squared per second. So if you've got your calculator handy, can anybody verify for me what's the Reynolds number that applies here if we've got 0.5 meters per second, 0.25 meter diameter pipe, and 1 times 10 to the minus 6th meter squared per second? 125,000. Okay, so the Reynolds number, RE, is 125,000. So that's 1.25 times 10 to the 5th. Okay, now you've got the figure there. See if you can find where do those two things come together on the figure. It's a logarithmic scale, so you need to be a little bit careful and thoughtful here about the logarithmic scale. Just as a refresher, the logarithmic scale is saying, for example, here's 1 times 10 to the minus 4th, 2 times 10 to the minus 4th, 3 times 10 to the minus 4th. So this is where things start, and as you move right, the quantities increase. And so then this is 1 times 10 to the minus, 1 times 10 to the 5th, 10 to the 5th, yeah, 2 times 10 to the 5th, and so on. So find the point of intersection where you're following this curve and the Reynolds number, and then you go to the left and find the friction factor. So did you sketch that out onto the figure? This is subject to interpretation a little bit. This is subject to whether you're using a pencil or a crayon or a big fat Sharpie or something. So we have other methods that are more precise, but a Moody diagram is good for quick and easy. So I got an F value of 0.022. And let me show you how I found that. I'm following this curve, and then also there's a line that goes up from 1.25 times 10 to the 5th. So 1.25 times 10 to the 5th is a little bit further to the right than halfway, because this is a logarithmic scale. It's not just right here, because you'll notice this is 1.5 times 10 to the 5th, but it's a little bit to the right of halfway, isn't it? Look at this one and that one, And the 1.5 is just shifted a little bit to the right because of that logarithmic scale. So 1.25, and I'm really splitting hairs here, but it probably starts about there. So a little bit to the right, a few pixels to the right. So we go up, and we look for the point of intersection with this curve. Oh, and I must have picked that so that it would be right on that line. Super convenient. We just go right over to the left, 0.022. Because it was this intersection with the 0.01 curve. Now, if you'd been between two of them, like if it was 0.0015, there's no guideline. So you just stay like halfway between this one and that one, if it's in the middle. So you'd say, all right, I'm just going to stay in the middle of those two till I get to my Reynolds number, and then I go straight left from there. Any questions on how to use the Moody diagram? Okay, you're going to use this on the homework assignment, so you could get started on that now. I'm sure you could have done it before, but it's a good refresher always to look at the Moody diagram. Because of how quick and easy it is to use, there are a fair amount of questions on the FE exam that utilize the Moody diagram. I was just down at the headquarters of NCES last weekend helping to write the FE exam. I'm on the environmental exam committee, so I get to see what the questions look like and the statistics and what kind of questions get good results and so on. So this is one that maybe is in the ballpark, the kind of thing that you could do in less than 4 minutes, which is what they're aiming for on the FE questions. Any questions before we move forward from this one? All right, this is one of your homework problems. And I just wanted to talk about it in general terms, give you a few key hints along the way. So there's water coming from a reservoir, and what we know is the flow rate is 1,000 gallons per minute. So in part, this is a units conversion problem. So you're going to have to convert from gallons per minute into cubic feet per second to really solve this problem well. They give you the diameter of the pipe in inches, but this epsilon, by the way, epsilon and K sub s are used interchangeably depending on the reference that you're looking at. So here, epsilon, that just means the equivalent sand roughness. The same thing that we saw as the K sub s on this one. So you're given a diameter, you're given the equivalent roughness, and so that defines for you where things start on the right-hand side of the Moody diagram. So what you're going to do here is you're going to determine what is the F value, using the same thing that we just did in this example. Find the F value, and then the whole point of determining the F value is that you put it into the Darcy-Weisbach equation. So this formula tells you how much energy loss there is. And does anybody remember seeing this energy equation back in fluid mechanics? It's similar to the Bernoulli equation, but distinct because you're accounting for friction losses. So this H sub F on the right-hand side of the equation suggests that water is flowing from 1 towards 2. There's a directionality. Water is flowing from this reservoir. So location 1, just for instance, maybe, is here at the top of the water in the reservoir. This would be location 1. And then location 2 would be at the top of this building, which we know the elevation is 100 feet. And we know that we want the pressure at location 2 to be 30 psi. So you know P2, you know Z2, velocity. You can neglect the velocity head at location 2. But you're just going to find out how high does the water need to be in that tank to overcome the pipe friction and provide the required pressure at 2. So this is just a direct application of the example where we're taking the F value that you find from the Moody diagram and then putting it into the Darcy-Weisbach equation. Those are hints that I think will help you out as you actually start working the problem. Okay, so consider water that's flowing through a pipe. If we were going to do a force balance on water inside of a pipe, what we could see would be that if we just consider some element of water in the pipe, you know, the water is on both sides of this element, but we're just drawing control surfaces around a pipe, and we're going to consider what forces are acting on some of the water in the pipe. So if we just take an isolated segment of water, there's going to be pressure in the pipe on the other side of that water. So here, if the water is flowing from 1 towards 2, there's going to be the pressure on the left side of it that's pushing in the same direction of its movement. There's the pressure on this downstream end that's resisting its movement by virtue of the fact that we've put our control surfaces and external forces are going in the opposite direction. There's the weight of the water acting downward. And then shear stress times perimeter times the length is the integrated effect of the resistance due to pipe friction. So shear stress times P, perimeter would be the circumference around that circular pipe, and then length would be the distance between 1 and 2. So we're just saying if you consider the entire surface area that water is in contact with, the entire pipe surface area, and multiply it by some shear stress, then that is the force that's being applied in the opposite direction of the water's movement. So the water's moving to the right, the shear force pushes to the left. It's always resisting flow. So we could do an equilibrium force balance in the direction of flow, and what we'd find is its equilibrium means it all equals out to 0. That once the water isn't accelerating, if conditions are flowing steady and uniform, the forces are balanced, that the change in pressure is going to be because of the shear stress that's applied due to pipe friction. That's why the pressure is lower downstream. In a horizontal pipe, when water is flowing from one location to the other, it flows towards the downstream direction because it's less pressure down there. And then the other way to think about it is the pressure is decreasing because of pipe friction. So a couple of definitions to supplement all of this. We can say that the change in pressure is due to the energy loss due to pipe friction. So here H sub F just means energy loss due to pipe friction. And if the cross-sectional area divided by the wetted perimeter is the hydraulic radius, so with those two things, what we can say is that the head loss due to pipe friction is because of a shear stress that's applied over some length relative to the hydraulic radius, and then also taking into account the unit weight of the water, gamma. If the conduit is circular, such that a pipe that's totally full all the way to the top, if it's got water in it, then the area is pi d squared divided by 4, and the wetted perimeter is pi d. I think we all agree to that. So then the hydraulic radius, if hydraulic radius is area divided by wetted perimeter, then it's going to cancel out the pi. It's going to cancel out one of the d's, so it's just d divided by 4. So the hydraulic radius of a pipe that's full is d divided by 4. So this further simplifies how we can relate shear stress and pipe friction due to energy loss. And where we end up, the conclusion here in the box, is this relationship between shear stress and S sub F, which is the slope of the energy grade line. As water is flowing from 1 to 2, the energy grade line is decreasing. There's less and less energy in the pipe, and so if you multiply the energy grade line by the hydraulic radius and the unit weight, that's how you can find the shear stress that's being applied to the fluid. So water moves from 1 to 2, it's resisted from that movement, and you can calculate the magnitude of the shear stress with this formula. I'll try not to belabor these derivations too many occasions, but this is an important one. I wanted to kind of draw your attention to that you can just do a force balance on some element of water flowing through a pipe and get to the relationship between shear stress and the slope of the energy grade line. And the same is true in open channel flow. It's not just closed conduit flow that this applies to. Things look a little bit differently, but in an open channel of water, you've got water in contact with the air. And so a little bit about these symbols here. See this triangle? The triangle and then these little lines under it? That means the air is touching the water. So that means a free surface of water, where it's not pressurized, it's just open to the Earth's atmosphere. So at the top of this, the pressure is 0, and then as you go down through the fluid, the pressure is increasing. So in open channel flow, the same kind of force balance can also be applied. And what you'll find is that shear stress is applied. So see this shear stress? As the water's flowing through a river, the river pushes back against the water's movement. It resists the water's movement. And there's an equilibrium between the slope, the energy loss, and the shear stress that's applied. So we'll get more into the open channel stuff in the second half of the class, later in the semester. But for now, we'll focus on some formulas that predict the effect of shear stress. We don't calculate the shear stress directly very often. Most of the time, we're going to be looking at the effect of the shear stress. Like, why is there pressure loss when water's flowing through a pipe? Why do we have to put in a pump to get the water from the treatment plant to here, to this building? The treatment plant is only about a mile upstream along the Ohio River, but we have to have booster pumps to overcome the effect of pipe friction and get the water here. And so different formulas for quantifying that head loss effect. So let's just play around with the numbers related to this shear stress calculation. Let's say that we have an inclined pipe. We've got a pipe where the water is flowing from 1 to 2, but the pipe is going uphill. The interesting thing is that the energy grade line decreases in the direction of flow independent of the pipe's orientation. It doesn't matter if the pipe is horizontal, or if the pipe is going downhill, or if the pipe is going uphill. As long as the water is flowing from 1 towards 2, the energy grade line is going to be going down in relation to the energy that's lost due to pipe friction. Okay, so let's do some calculations here and calculate the slope of the energy grade line and then the pressure change over 100 meters of pipe. So we've got the formula for shear stress, the formula for hydraulic radius, and so on. Just because we've only got about 10 minutes left in class, I think probably what I'll do is, rather than giving you time to work these calculations, which would be my preference, I think what I'm going to do is just bring up the solution and we'll look at it together. And so you can get a feeling for what these calculations look like. Let me see if I've got these examples at the ready. All right. So what we want to do in this example is find out S sub F. We want to find S sub F, the slope of the energy grade line. And we know the shear stress is 45. So shear stress is known. Since it's water, what's the unit weight of water in SI units? 9810 newtons per cubic meter. Good. Hydraulic radius, R. Well, that depends on the fact that it's 150 millimeter diameter pipe. So the first thing that I do in these calculations, and I say, let's calculate the hydraulic radius. I did it the long way. I could have just done d divided by 4, but I did the hard way just to prove to myself that it works. So if you've got the area of a 0.15 millimeter pipe divided by the wetted perimeter, here we get the hydraulic radius 0.0375 meters. Well, turns out that's the same if you just do diameter divided by 4, 0.0375 meters. So we know hydraulic radius. We know that gamma is 9810. We know that the shear stress is 45 newtons per meter squared. So just substituting that into the formula, I rearranged the formula to solve for S sub F. Here's the thrilling conclusion, that the slope of the energy grade line is 0.12232 meters per meter. So that's vertical per horizontal. That's for every meter of distance in the horizontal direction, you're going to lose 0.12 meters of energy vertically. So that's the slope of the energy grade line, is this decimal. So the thing that's interesting is that the slope of the energy grade line is independent of the pipe slope. If it's an enclosed pipe, the same isn't true in open channel flow. If you've got a river, the slope of the energy grade line is going to be the same as the channel slope if it's steady, uniform flow. But in closed pipe flow like this, you can have the pipe going uphill and the energy grade line going downhill, and we've just seen this example that confirms it to ourselves. So that was the first part of the example. Any questions on these first calculations? I see a number of 3-ring binders today. That's good. Some of you have already printed out the notes. That's good. I haven't yet got together the description of what you should have as far as the binder, but we'll talk about that next week, this 2% of your final grade that goes for the binder. Okay, so the next part of the example was, what is the pressure change over 100 meters of pipe? Okay, so we know S sub F is 0.122. 100 meters is the length, so we can calculate H sub F. And then with H sub F into the energy equation, we'll be able to calculate the difference between P1 and P2. So that's just kind of like the overhead view of what we're doing in part B. We know S sub F, so let's use that to find H sub F. And then once we have H sub F, we'll substitute it into the energy equation. Of course, there's no pump, so the H sub P term will cancel out. And if we're talking about location 1 and location 2, and the diameter of the pipe is the same, how will the velocity of the water change? Assuming that this is an incompressible fluid and the diameter is the same, what's the difference in velocity between 1 and 2? I see someone shaking their head in the negative. You're right. So what were you saying?
Nothing.
There's no difference. Yeah, the velocity will stay the same. If you've got an incompressible fluid, the velocity can't change if the diameter is the same. So V1 and V2 are equal to each other, so they're just going to, as you'll see, drop out of this formula. It'll simplify. So let's actually look at the calculations. Okay, so here's the energy equation. I didn't even bother writing the pump term because there's no pump, but V1 and V2 cancels out because the two velocities are the same. And if we assume, let's say that Z1 is 0, Z2 is 10 because the slope of the pipe is 0.1 meters per meter. So if we're talking about 100 meters of pipe length, then the vertical increase in length of the delta Z is 10 meters. So if Z2 is 10 meters and the H sub F is 12.2, we substitute all of that into the rearranged version of the energy equation. We're trying to find the change in pressure. How much does the pressure change? It's going to change for two reasons. It's going to change because of the elevation difference and also because of energy loss due to pipe friction. And both of those changes are in the same direction. Like, just think about it conceptually. You remember the hydrostatic equation. Like, if the water wasn't moving at all, if the water was just stationary, the pressure here would be less than the pressure here because it's higher up in the fluid. You remember that, right? That if you have a tank, that the pressure is higher, lower in the tank. The pressure is less as you go up through a fluid. So comparing 1 to 2, there's two reasons why the pressure is less at 2. And the first of them is because location 2 is higher up in the fluid, so the pressure is decreasing due to the elevation difference. And then the other reason why the pressure is less at location 2 is because it's downstream. The water has been flowing through this pipe, losing energy due to pipe friction. So the pressure is decreasing in the direction of flow for those two combined reasons together. We had 10 meters of head being lost due to an elevation change, and 12 meters of head being lost due to the pipe friction, and those things collectively account for a pressure decrease of 218.1 kilopascals. So that ultimately is the answer to part B. 218 kilopascals is how much pressure changed through the pipe. So what questions do you have about that example? I'll remind you, since I record these, you know, if I'm flipping through the slides too quick or you didn't get to write down all of the example, you can always just pull up the video and copy the rest of the solution later on after the fact. Okay, so Bernoulli's equation versus energy equation. I already alluded to this earlier that the energy equation is similar in appearance to the Bernoulli equation, but it accounts for head loss due to pipe friction. So Bernoulli's equation would say that if the velocity decreases in a pipe transition, that the pressure should increase. And that thing will still happen in the energy equation, but the energy equation also accounts for the effect of energy loss due to pipe friction. So if there was a pipe like this where the diameter was the same, Bernoulli's equation would say there's no change in pressure, but we can observe that change of pressure in the real world. We know it happens. And so the energy equation is what we need to account for the energy loss due to pipe friction. So the change in pressure for a horizontal pipe is because the pipe is resisting the movement of the water due to the no-slip condition. So all the different equations that we're going to be going through to learn different ways to estimate that effect of the energy loss due to pipe friction, we'll spend the first couple of weeks just talking about estimating the effect of energy loss due to pipe friction. You may recall talking about piezometers in fluid mechanics. These are the simplest device that you can have for measuring pressure in a pipe. Like if you just puncture a pipe and water starts spraying out from the hole, but then you put a tube into that hole, water is going to rise up in the tube to a level that reflects the pressure in the pipe. So water level just rises to come into equilibrium with the pressure in that pipe. That's a piezometer. And if you had two piezometers in a pipeline, you'll notice that as water flows from one direction to the other, that the water level is lower downstream due to pipe friction. So the hydraulic grade line is the combination of the pressure head and the elevation head, whereas the energy grade line also accounts for the velocity head. So just looking at this change of hydraulic grade line over time, when you take into account the energy loss due to pipe friction, there has to be some proportionality factor, F. And that's the F value that we got from the Moody diagram today. Unfortunately, that's all the time we have for today. We'll have to talk about shear velocity in class on Wednesday. Remember that you've got a homework assignment on your plate right now that you can begin. We'll go over some more examples in Friday's class that will help you to solve that, but I encourage you to get an early start.